Hello, can you hear me? You
You
can
can
just
just
type
type
on
on
the
the
chat.
chat.
Okay,
Okay.
okay,
Okay.
okay,
Okay.
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 That's
That's
okay.
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 I'll
I'll
begin.
begin.
My
My
name
name
is
is
Anvesh.
Anvesh.
I'll
I'll
be
be
the
the
TA
TA
for
for
the
the
course
course
IFM,
IFM,
Interfacial
Interfacial
Fluid
Fluid
Mechanics.
Mechanics.
You can, I
I
hope
hope
it's
it's
visible.
visible.
Uh,
Uh,
okay.
okay. I will
Just
just
wait
wait
for
for
a
a
few
few more
minutes.
minutes.
Okay.
Okay.
I had
I
a
had a
couple
couple
of
of
questions.
questions.
Are
Are
you
you
in
in
your
your
first
first
week
week
or
or
second
second
week?
week?
Uh, can
Can
you
you
hear
hear
me?
me?
Okay, okay,
Okay.
okay.
Okay. Okay.
But
But
this
this
is
is
the
the
first
first
doubt
doubt
class.
class.
So
So
before
before
we
we
start,
start,
do
do
you
you
have
have
any
any
doubts
doubts
or
or
you
you
have
have
any
any
structure
structure
in
in
mind
mind
as
as
to
to
how
how
to
to
go
go
ahead
ahead
with
with
this?
this?
Yeah. Okay.
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 That's
That's
good.
good.
Uh,
Uh,
the
the
first
first
two
2 weeks
weeks are
are
primarily
primarily
a
a
recap,
recap,
and
and
the
the
second
second
week
week
slightly
slightly
starts
starts
off
off
with
with
the
the
main
main
agenda
agenda
of
of
the
the
course.
course.
With
With
regard
regard
to
to
the
the
final
final
exam,
exam,
the
the
final
final
exam
exam
would
would
be
be
an
an
MCQ
MCQ
exam.
exam.
I'm
I'm
not
not
sure
sure
the
the
number
number
of
of
questions,
questions,
but
but
the
the
course
course
is
is
meant
meant
for
for
postgraduate
postgraduate
level,
level,
so
so
it
it
will
will
be
be
fairly
fairly
difficult.
difficult.
But
But
howsoever,
howsoever,
the
the
questions
questions
and the
and the
assignments
assignments
are
are
doable
doable
if
if
you
you
go
go
through
through
the
the
lectures.
lectures.
And I
I
feel
feel
this
this
is
is
a
a
really
really
unique
unique
course,
course,
and
and
it's
it's
quite
quite
helpful
helpful
if
if
you're
you're
working in
working
the
in the
domain.
domain.
Does
Does
that
that
answer
answer
your
your
question?
question?
I'll
I'll
wait
wait
for
for
a
a
couple
couple
of
of
minutes,
minutes
and
and
then
then
I'll
I'll
start.
start.
Also,
Also,
in
in
regard
regard
to
to
the
the
doubt
doubt
classes,
classes,
so
so
for
for
the
the
first
first
two
two
weeks,
weeks,
you
you
seemed
seemed
the
the
questions
questions
are
are
okay.
okay.
Okay,
Okay.
the
The
scope
scope
of
of
research.
research.
So
So
many
many
a
a
times
times
when
when
I
I
started
started
off
off
my
my
research,
research,
I
I
had
had
mostly
mostly
been
been
exposed to
exposed to
flows
flows
which
which
are
are
single
single
phase,
phase,
and
and
the
the
course
course
that
that
you're
you're
taking
taking
up
up
is
is
unique
unique
in the
in the
sense
sense
that
that
so
so
up
up
till
till
now
now
you
you
have
have
probably
probably
the
the
most
most
fundamental
fundamental
problem
problem
that
that
you
you
might
might
have
have
looked
looked
at
at
will be would
would
have
have
been
been
a
a
lid
lid
driven
driven
cavity.
cavity.
So
So
in
in
this,
this,
if
if
you
you
notice
notice
that
that
if
if
you
you give
give, if
if
we
we
take
take
0
0
comma
comma
0
0
here,
here,
the
the
and
and
1
1
1
1
comma
comma
minus
minus
1
1
1
1
comma
comma
1
1
minus
minus
1
1
comma
comma
1
1
minus
minus
1
1
comma
comma
minus.
minus 1.
So
So
you
you
will,
will,
sorry
sorry
for
for
the
the
handwriting.
handwriting.
I'm new to
Go to
this.
this.
So if you notice here, then the walls are fixed. So you know where the wall is. But in problems that are being dealt in this course, the interface is one of the unknown, and there is fluid on either side of the interface. So here it's row B, here it's row A. So essentially, you're solving, if you want to look at it, this is you're solving for both this fluid as well as this fluid. And then additionally, the USP of this course is that you also learn how to deal with interfaces. That is this. So the unique part about this is that interface position is not fixed, and that needs to be solved as one of the solution part. And if you, as you might have seen in the course, there are many phenomena like a sessile drop, which will be looked at. This is a sessile drop, and you want to know how this behaves, how the drop sits on the solid substrate, and what are its dynamics. So one question will be, what is the static behavior of the drop on a flat surface? But what if we put the drop on an inclined plane? You will expect the drop to slide down, but it's not as simple as a solid body problem. You have to solve for the fluid inside, and it's crucial to understand how it is done, where the interface deforms. Additionally, there is a very, you might have seen this. Okay, I'll try to make a simplistic diagram. Okay, this is your water tap. So when the water flows, you might have seen it will make such a pattern, and then it drops. So how does this work? At what length L you see drops forming? Uh, these are some of the problems that you will be capable to look at once you finish the course. Uh, so researchers, specifically chemical engineers, mechanical engineers, and in some cases civil engineers, look at such a phenomena. So in civil engineering, you will see that there is a porous media bed. So it's, again you will, so this is two fluids, row A, row B. So you will be looking at how is the interface adjusting to this. This kind of research is crucial for civil engineers. Chemical engineers primarily look at drops, bubbles, and jets. This is a sort of a jet, this problem. So these are some of the problems that you will be able to look at, and this course helps you do it. These phenomena can't be understood with a single phase kind of setup. I hope that answers your question.
Wow.
Okay, I'll begin. I think I'll go over some questions. I didn't have an idea what to go over. So I just so let's look at the question in week 0. I think uh, the question was the expression for momentum in the y direction, I believe, in the y direction. Y direction. Okay, before that, have you submitted the week 0 and week 1 assignments? Okay. Okay. So, okay, another. Okay, week 2 also. Okay, okay, all right. Okay. Uh, is this okay? So I believe these are stuff that you would already know. Okay, okay. Kesha says 100 and week 0. Okay, okay. But I believe these are these expressions are known to you from preliminary courses in fluid mechanics. So, but still, I'll just go over del V by del T plus del V by del X plus del V by del Y plus del Z equals to minus del V by del 5 plus so if you divide the above equation by rho everywhere, you'll get the form. So, but I would like to point out before we do the division. So this part is the unsteady part. This part is the inertial term. Um, this is the viscous term. So if you divide the equation by rho, you will get the form that is there in the options. So this is another thing I wanted to go over. There was a question on Buckingham pi theorem, I believe, in week 0. So I before we go there, I just wanted to give you a brief question as to how to deal with problems. So the question, okay. Sorry. So this is a problem where there's a layer of fluid. There's a layer of fluid, and then there is v is the velocity of the wave speed, and then there is gravity. So this is a simple problem, and then the goal is to understand the goal is to understand scaling and Buckingham's pi theorem. So I just don't say Buckingham pi theorem because Buckingham pi theorem is at this level, it's like solving a problem blindly. And then you're at the postgraduate level where you should have an understanding of how to deal with parameters in a study, in a problem, in a phenomena. So first we look what are the parameters in the given problem. So parameters. So what are the parameters? The wave speed, the depth. Okay, so this h, the h here is the height of the wave. The d is the depth of the fluid from the solid surface. So that is the depth. Then we have gravity, and then we have rho air, which is at the top, and then the rho of fluid. Density. Rho is the density. Okay. So what are the okay? These are the parameters in the problem. There could be more parameters where on the interface we say there is surface tension. But currently in this problem we are not looking at the surface tension effects. So the key is that while we are analyzing this problem, we are not taking surface tension force to be dominant. We're just analyzing the problem just by the parameters that are given. So for the time being, we're not worried about uh, surface tension. We're not worried about this. Okay. So in Buckingham pi theorem, I suppose you might have learned Buckingham pi theorem, and then in that you look at fundamental quantities. And the fundamental quantities are mass, length, and time for us. And then you can write all the dimensions of all the parameters that apply there. So now we'll look at how to analyze the problem here. So firstly, we notice that the dimensions of rho is okay, m l minus 3. And then if you look at all the other parameters which are marked in red, none of them have the term m. So if we think about it, what are we trying to do in Buckingham pi theorem? What are the pi terms? Okay, before that, I'll just tell you the pi terms. Pi terms, how many pi terms are there? Pi terms is equals to the total number of parameters, which are 6 here. 1, 2, 3, 4, 5, 6. 6 minus 3, which is equals to 3. This means we will have pi 1, pi 2, pi 3. Now, the normal procedure of going ahead with Buckingham pi theorem is you write down pi 1, and then you write down each term, and then you basically set them to 0. You get a algebraic system of equations, which we'll see ahead, and then you basically get the dimensionless groups, which are important to analyze a system, to analyze a problem like this. So I was talking about rho density. So you see that density has the term m, basically mass, and all the terms in the red don't have mass anywhere. So if we think about it, one of the non-dimensional group should be rho a by rho. Straight away we can say that if there is rho in one of the pi terms, the only way it can be non-dimensional is it has rho dividing it, because kg needs to be cancelled. So one of the pi terms you can get is rho a by rho. Similarly, if you think about it, the second non-dimensional group can be written as h by d or d by h. Now again, as a researcher yourself, you will know that uh, h will have smaller values and d will have larger values. So this is a smarter choice to make. And then for the third pi group, you need to do the actual Buckingham pi, or there's another method that I'll go over. But first we'll do the Buckingham pi method of solving it. So how will we do that? We'll write V uh, will take. So now we will replace with L T minus 1 A into L B into L T minus 2 C into M L minus 3 T. We get our algebraic equations by balancing the power. So for M we will have, okay, okay. For M we have T is equals to 0, and then if we write L for L, it will be A plus B plus C. Okay. I think I made a mistake. Um, okay. Okay. So when you're doing Buckingham pi, you only take three. One of them is a free parameter. I taken all three. So basically here there won't be anything. There will be just in depth, gravity, and density. There will be only B, C, D exponents. So B plus C, B plus C minus 3D equal to 0. And then finally time is minus 1 uh, minus 2C equal to 0. So we need to solve the set of algebraic equations. From here, from here we get from the third equation we get C is equals to minus 1 by 2 minus 1 by 2. One second. Just need. Okay. Uh, I'll resume. B is equals to 0. So basically that will give us B which is equal to um, equals to minus 1 by 2. So B was depth and C was gravity. By replacing, we will get the expression V is equals to under root B G. So the crucial outcome of this analysis is that the wave speed does not depend on density, and this has been verified for such a setup where surface tension is not important, is not playing a role. So This is a one of the method of doing it. The other smart way of doing this, that is why I have said scaling, is that to look at what are the forces in the problem. So if we look at this problem, what are the forces that we have? So I'll just write it here. So by looking at the problem, we see that the forces, primary force, the forces that are at play here is inertia, that is the wave is moving, and then the gravity down here. So another way of arriving at the same result by scaling is to say that phi 3 is a balance of forces, the inertia force by the gravity force. So now how do we write the inertia force? Uh, if you have seen the Navier-Stokes equation, you can write the inertia force as rho u del u by del x. This is the inertia force, and the gravity force is simply rho g. This all of this is being done at per unit volume. So the volume gets away. This is a per unit balance. You can see this here in the momentum equation that I've written. This is the inertia term, which is basically u dot del u times rho. So if you straight away rho gets cancelled, and then if you say that u scales as velocity v and the length x scales as the depth, then you can write the same thing here as u is replaced by wave speed, and then again the del u gives us another u, and bottom it gets d, and then here again there is g. So here again we'll get is equals to pi 3 basically is v square by g t, which can be written as v square equal to g t, which can be also written as v down the road. So, so it's crucial that here in the second method that we have taken, you have an understanding of what are the forces that are at play in the phenomena and how balancing them gives you non-dimensional groups. And these non-dimensional groups help in analyzing the problem. And you will see this as a recurring theme in the course, where such an analysis is done to first look at look first done to identify what are the parameters that are there in the problem, because soon you will be dealing with problems where there is surface tension, and then you have to see what force balances which force in different regimes. So the number of terms will increase and the number of non-dimensional groups will also increase consequently. And this this kind of an analysis helps us get insight into the problem and allows you to break the problem into smaller parts, which is crucial for us as at one point you can balance two forces for a simplistic analysis like this. Like here in this problem, we can get in surface tension. But if you think of oceanic flows or open channel flows, where the volume and length scales, the depths are of the order of okay, sorry, um, are of the order of kilometers, kilometers, then the surface tension doesn't play an important role there. So such kind of analysis taking in and taking into account surface tension doesn't make sense. So I hope this is useful and this will be a recurring thing. Okay, I was saying first you identify the parameters that are at play in the phenomena, then you see what are the fundamental quantities, and then you make an educated guess as to what the non-dimensional terms will be. If okay, yeah, I hope this helps. Now I would just like to ask, are you all aware of Einstein notation? Anyone, if you could answer? Okay, okay. Keshav says yes. Okay, I'll just briefly go over it. I won't go into details. Um, so if we have a vector u, we basically know its component form will be 1, 2, 3. Okay, so Einstein notation basically helps us write this in a compact form. So instead of writing the entire expression here, you can write it as summation I is equals to 1 to 3 5. So this in shorthand notation can also be written as UI. Then basically in Einstein notation, the index I here, which is a dummy index, whenever it is repeating, it is summed over all the three real axis coordinates, basically 1, 2, 3. I goes from 1, 1, 3. So another way to just write this is by some special symbols are also there. I would like to go over them. Delta. So second order tensor, and basically delta ij equals to I equals to j, then it is 1. If I is not equal to j, it's 0. So if, for example, if we have, let's say, ui delta ij, then we know from Einstein notation that, sorry, from Einstein notation, we can say I goes from 1 to 3, I delta j, which will be just equal to u1 delta 1 j plus u2 delta 2 j plus u3 delta 3 j. So if we again write this, we expand j as well. So then the terms that survive from these will be just, for this case, only when j is equals to 1, the term survives, as rest of the times delta 1 2, delta 1 3 is 0, is identically 0. Similarly, j equal to 2 survives here, j equal to 3 survives here, rest of them are 0. So, so then this will be u u1 plus u2 plus u3, or simply you can say that uj. So we see that ui delta ij will give uj. Similarly, we have another third order tensor, alternating. So which looks like, say, good. And then if we write it down, sorry, system ijk is equals to 1 when ijk are in order, that is 1 2 3 2 3 1 and 3 1 2. Are if the alternative tensor is identically 0 when there are repeating terms, repeating indices, and minus 1 when I, j, k are out of order. That is 2 1 2 1 3 3 2 1 1 3 2. So these are some of the, this is crucial for even fluid mechanics, but here in this course, these concepts will be looked at, and I hope I could just go over them once. Okay. As you have not submitted the week one, have you the week one assignment, is the due date over or is it still open? Okay. Okay. So okay, do you have any further questions? I had I thought I'll go over week one questions, but as you have not submitted, I can't go over them. But from next week onwards, I'll take up, if you have doubts, I'll take up both week one and week two as well. So you have any doubts? You can